Okay, picture this. You're sitting in your Cambridge Physics 9702 exam, and you've basically got three different strategies. Think of them as three doors you can walk through to answer a question. But here's the catch. Only one of those doors actually earns you the marks. The other two, they're total traps. They will absolutely cost you points, drag you right into the danger zone of those brutal grade boundaries, and give you a massive confidence shock when you finally get your paper back. So today, in this explainer, we're going to unlock the only door that actually matters when it comes to mastering crystal symmetry and securing those high band marks. Let's get into it. So, which of these doors is actually going to get you the marks on an extended physics explanation question? Well, let's look at the three doors trap. When a question about crystal structure pops up, most students panic and run straight through door number 1 or door number 2. They decide to just memorize a bunch of labels or state random definitions entirely in isolation, kind of just hoping the examiner will give them the benefit of the doubt. Let me tell you right now, the examiner doesn't. If you ignore the internal physics, you literally lose the marks. It's really that simple. To win here, you need door number 3, which requires a totally different way of thinking about solids. To find that right door, you absolutely have to embrace what we call the microscopic rule. We always have to start from a visible physical phenomenon and work our way backward down to the microscopic picture. Real materials behave the way they do on the outside purely because of the atomic or carrier level action happening on the inside. So, if you want to explain why a material is strong or conductive or super brittle, you can't just wave your hands and say, oh, because of its structure. No, you have to explain the actual atomic choreography happening right beneath the surface. That brings us to crystal symmetry. And listen, this isn't just some static label you memorized from a textbook glossary. It is a practical, active, physical phenomenon. It's the internal arrangement that controls three massive, undeniable factors: packing, bonding direction, and defect tolerance. Think of it as a solid's active blueprint. Once you realize that crystal symmetry dictates exactly how a solid responds to physical forces, or thermal energy, or electrical fields, you stop seeing it as just a vocabulary word. You start seeing it as the absolute master key to understanding material behavior. Now, how do we use this? This understanding actually translates directly into an unbreakable revision tool, and it uses 4 rapid memory triggers. Next time you're revising, you should be able to answer these 4 prompts out loud purely from memory. Number 1, what is it? Number 2, what physically changes inside the solid? Number 3, what measurable consequence can we actually observe outside the solid? And number 4, where does this matter in real-world technology? If you can just fluidly answer those 4 questions, your grasp on the topic is going to be rock solid, totally secure enough to withstand the pressure of the exam hall. And going through those triggers brilliantly illustrates our very first master framework. We call this the layered physics method. And it is exactly what Cambridge examiners are actively hunting for in your extended answers. You don't just jump straight to the finish line. First, you start by defining the idea. Then, you step down to describe the microscopic mechanism. We're talking the atoms, the bonds, the carriers. Next, you step back up to identify the measurable consequence. And finally, you connect that consequence to a specific application. It's a perfectly structured journey, from the invisible, tiny atomic level all the way to a visible, tangible device in the real world. What's really fascinating here is how we can map these microscopic consequences directly to high-stakes technologies. Let's think about electronics. The microscopic defect tolerance of crystal symmetry is exactly what allows us to manufacture highly precise semiconductor wafers. Or look at energy systems. The highly specific bonding direction within the crystal is what dictates the extreme heat and stress resistance needed for turbine blades. And in aerospace, the internal packing efficiency gives structural alloys their crucial strength-to-weight ratio. See what we're doing? You are connecting the absolute smallest building blocks to the absolute largest industries on the planet. Now, if you can master that micro to macro connection, you're honestly already ahead of about 80% of candidates. But hang on a second. In just a moment, I'm going to reveal the exact examiner clue that changes your answer completely. It is a fatal trap that catches even the top students totally off guard. But before we get to that, you need the elite framework that's going to make that specific clue blindingly obvious when you're sitting there taking the paper. To conquer the final boss of this topic, you really have to layer your physics with a specific answer framework. You want to construct a highly disciplined paragraph. Here's how. First, you state the concept clearly. Second, you provide the evidence or data required by the question. Third, you apply your scientific reasoning. And yep, this is exactly where your microscopic mechanism comes into play. And finally, you lock it all in by using specific examiner wording. Let's be real, this isn't about writing some long, rambling essay. It's about engineering a surgical, high-retention response that literally leaves the examiner no choice but to give you full marks. Let's look at an example of where things go wrong. Consider this flawed student answer. Crystal symmetry makes the material strong, which is why it is used in aerospace. Ask yourself for a second, what is actually wrong with this? Because on the surface, it sounds totally okay, right? I mean, it states a correct term, crystal symmetry. It states an application, aerospace. But it completely misses the microscopic mechanism. It just jumps from step 1 right to step 4, entirely skipping over the internal physical reality of the solid. In an exam, an answer like this gets 0 marks for explanation. Absolutely 0. The fatal error here is just relying on a scattered collection of facts and macro-level observations. You just can't do that. A top-band answer, by contrast, is a disciplined paragraph. It specifically links the atomic structure and the internal mechanism directly to the device performance. It tells a complete, unbroken story of cause and effect. It proves to the examiner that you understand exactly why the material behaves the way it does, rather than just stating that it does. And that right there is the hidden examiner clue we were talking about earlier. This is the examiner trap. If you provide a brilliant, perfectly accurate real-world application, but you do it without explicitly linking it to the underlying microscopic reason, like the packing or the bonding or the defect tolerance, you will lose the marks. The examiner is literally testing your ability to connect the invisible cause to the visible effect. If you break that chain, you fall right into the trap. But even armed with this crystal symmetry master key, and even knowing how to perfectly structure your answers for this topic, an unresolved problem still remains. Door 2 is about to open. There are other fatal traps lurking deep in the 9702 examiner reports that you probably still don't know about. We're talking about mistakes that thousands of students make every single year simply because they don't understand the underlying psychology of the mark scheme. So, to make sure you don't fall into those remaining traps, watching our next explainer is your absolute mandatory next step. Make sure you subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to master the mark scheme and really excel in your Cambridge examinations. You need to know exactly what the examiners are complaining about year after year so you can be the exception to the rule. Which leaves us with this final thought as we wrap up this explainer. If a tiny gap in your crystal symmetry logic, like just missing one single microscopic link, can entirely derail your grade on a 5-mark question, what other hidden traps are waiting to trigger a massive confidence shock in your next exam paper? Keep questioning everything, keep connecting the micro to the macro, and I'll see you in the next explainer.